When it comes to drawing organic molecules, especially the alkane, alkene, and alkyne series, what you want to focus on in your reference table is basically table P and table Q, because those are the two tables that are going to help you out definitely with the number of carbons, so you can create your parent chain, and then you can determine on how many hydrogens you actually need, or if you're gonna kind of reverse engineer it to figure out what the names are and to figure it excuse me, whether it follows under the alkane, alkene, or alkyne series. You have the formulas right there. And so if you look at those three first, the alkanes are going to be all single bonds. So anything that you see between a carbon to carbon, don't worry about the hydrogens right now, but don't worry, or what you're focusing on is any carbon to carbon bond, if it's single, is typically going to be an alkane. If there's a presence of a double bond, which is designated by a double line, that would be an alkene. And then a triple bond designated by a triple line would be an alkyne. Now, if you notice in the process, there, for example, is 6 hydrogens here. There's 4 in the middle one, and there's 2 in the bottom. They keep losing 2 in each successive series. Now, these are called homologous series because the general basis and backbone is the same. So 2 carbons, 2 carbons, 2 carbons in this example. So we have ethane, ethene, and ethyne. And the big difference in the formula, so we have C to the N, again, where N represents the number of carbons. And then hydrogen is just 2 times N plus 2, or just 2N or 2N minus 2 for each of these. So if we substitute any value, it doesn't matter what you have. If I told you 50 carbons, I could figure out what the formula would be for an alkane, alkene, and alkyne just by plugging it in. It would be C50, because N would represent 50, and then 2 times 50 is 100, plus 2, there would be 102 hydrogens if it was an alkane. If it was an alkene with only one double bond, it would just be C50H100. If it was an alkyne with one triple bond, C50H98, because I would have to do 2 times 50, which is 100, minus 2 is 98. So when you're looking, again, you want to base it on table Q to figure out if your ending is going to be ANE for alkanes, and you're going to see all single bonds, ENE for the alkenes, and it's going to have at least a double bond, or YNE or INE for alkynes, and it's going to have at least a triple bond. Now, as far as the basic numbers of what you would ever have to do on the Regents exam, naming or drawing, only up through 9 and basically 10 in reality. So the prefixes are going to be different for each of those, so you recognize which one is which. So meth is 1, F is 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10. Now, some of these you may be familiar with. For example, in math class, for example, a pentagon has 5 sides, an octagon or an octopus has, associated with 8. Decades, for example, 10, or decagon would be a 10-sided object. And so some of them are familiar, some of them are probably new to you. And so I just want to go through some of the examples. If you have the first initial series, if we're just dealing with the alkanes, we have C to the N, H to the 2N plus 2. And so all of these materials, let's just say if I had a carbon, let's just say we had 7 carbons, okay? If we plugged that in the formula, C7, and then if I plug in 2 times 7 is 14 plus 2 is 16, H16, when we draw that, the simplest way to draw it is just a straight chain. 1, 2, 3, 4, 5, 6, 7. Again, 1, 2, 3, 4, 5, 6, 7, all single bonds. Now, what you learned earlier in the year with bonding, that carbon is special and that carbon has 4 valence electrons, and so it can bond up to 4, or with up to 4 different atoms. It can have double bonds, it can have triple bonds, but it can bond with up to 4 different atoms, including other carbon atoms. And so each carbon needs to have 4 bonds, and so we need to fill in the rest. And so our hydrogens are going to be all around. And this, again, is the simplest structure, just to go all the way around and continue to fill those in. And so as we look at those, 1, 2, 3, 4, 5, 6, 7. So there's basically 7 on top and 7 on the bottom for each of the respective carbons. So that's 14, plus there's the 2 at the end. That plus 2, there's 2 extras at the end. So we have our total of 16 hydrogens. Again, drawing alkanes is simple. All you really have to do, if you're given a name, if you just look up the name of the material, you just find the prefix that's associated with that alkane name, figure out how many carbons it is, and draw out that many, and then fill in the rest with hydrogens. So for example, if we had propane, I'd say, okay, well there's prop. Prop means 3. So for example, propane. Propane is the gas that's in your gas grills. Maybe sometimes you see it called LP gas, which they call liquid propane. It's stored under pressure, and then once you release the valve, the gas is released. It doesn't squirt out a liquid, obviously. And the next one up, bute, right here is butane. That's the same liquid you see if you have a clear cigarette lighter or like the long extension candle lighters. That would be butane liquid put under pressure, and once you press the button, it releases the pressure and it goes back in a gaseous form. So prop means, of course, 3, so that would be C3, and then if we just double it and add 2, that would be C3H8. 1, 2, 3. And then I'd have basically 3 on the top, I'd have 3 on the bottom. But if you notice that this carbon right here, if we look left, up, down, and right, that has 4 bonds, but the others don't. So we have to have those other hydrogens in there to actually get the correct and appropriate bonds. So alkanes are probably the simplest ones to name. Things that you have to keep in mind, in that reality, this is not how they always look. They don't look linear. They don't look perfectly straight. In reality, if we were to actually make the molecule in a lab setter with a lab kit, you might have a carbon, and then a carbon, and then a carbon, and then a carbon. That's 3, 4, 5, 6, and 7. And it doesn't even have to be that direction. If we wanted to really go, remember, these molecules can bend on themselves. So if you've ever made molecules in lab, you know that, of course, maybe this bends this way, and then this bends this way. So we got 1, 2, 3, 4, 5, 6, 7. It doesn't have to be perfectly straight, but these are really the same exact molecules. This is a more accurate depiction. And three-dimensionally, I don't want to go too crazy in my drawings, but you know, if we drew one almost like with depth coming out at us, there'd be a hydrogen coming out at us one way, and maybe another hydrogen coming out at us another way on this side. And so now this carbon has 4 coming off of it, where this one might have, you know, one kind of hydrogen coming at us, another hydrogen coming at us, but then it might have another one kind of going in the distance, kind of going backwards. And so we have all these hydrogens that are coming and going in different directions, and this makes the molecule a little bit bulkier and a little bit more you know, of an issue if you're trying to actually have it react with something. And these, again, if you've manipulated the molecules, in class, you know that they can bend and move around. And so each of these, of course, would be going in all different directions. So just keep that in mind. And then, of course, the simplest structure would be just the skeletal structure. 1, 2, 3, 4, 5, 6, 7. Again, 1, 2, 3, 4, 5, 6, 7. As I teach my kids with the skeletal structure, there is no need for all the hydrogens. They're just assumed to be there. The only thing that's listed is the bare bones or the backbone, hence skeletal. And so at the ends and at the bends are where you would see a carbon. So at these two ends, in reality, there's a carbon at each of those places. And then at the bends, there's one there, 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 and there. So we had 2 at the ends and we had 5 at the bends for a total of 7. So all 3 of these, 1, 2, 3, they are all really the same exact thing. Okay, they are all really the same exact thing. They're all different ways that you can draw organics. If you're required to draw all the hydrogens, you can do that. If you just drew this, if you just had the carbon chain, sometimes the state regents exam even accepts just that. Or for example, if you had 1, 2, 3, 4, 5, 6, 7, this is the same thing as well because it's 7 continuous carbons. If I were to take my pencil, I could continue to draw through those without lifting that pencil up once. So that's one continuous chain. So when you're drawing the alkanes, again, it's relatively simple. Just find the total number of carbons that you need from table P, based on your prefix or the other way around, and you can again start to do your chain. Now, if you're given the number of carbons and you have to name it, the same thing holds true. All you have to do is go through and count. For example, okay, if I was just given this drawing, I'd say, okay, there's 1, 2, 3, it's all single bonds, so I know I'm dealing with an alkane. And then I'd go over to 3, and I see 3 is related to prop, so this is propane. If I saw this one, 1, 2, 3, 4, 5, 6, 7, I'd go and I would look and see that 7 is related to hept. So this, of course, all of these are going to be heptane. Okay, these are all heptane. And it doesn't matter how we draw it, it's all the same because it's just one long continuous chain. Now, if you go more in depth and you start dealing with branches, then that's going to be a different story.